Hello, and thank you for standing by, and welcome to our webinar titled Designing Fast Data Architecture for Big Data Using Logical Data Warehouse and Data Lakes. My name is Lisa Snyders, your host for today's session. For our presentation today, we'd like to welcome Kurt Jackson, Platform Lead with Autodesk. Kurt's responsible for standards, governance, and setting the good how-to patterns for several mission-critical IT tools. Kurt has spent his entire career in IT with experience in government agencies, cellular communication, and software companies. We also have with us today Ravi Shankar, CMO with Denodo. Ravi is responsible for Denodo's global marketing efforts, including product marketing, demand generation communications, and partner marketing. Ravi brings to his role more than 25 years of proven marketing leadership from enterprise software leaders such as Oracle and Informatica. In today's session, Kurt Jackson will share how Autodesk designed a modern fast data architecture as a single unified logical data warehouse, data lake, using data virtualization and contemporary big data analytics like Spark. Ravi will follow his presentation to cover why a logical data warehouse and logical data lake can provide equivalent performance to that of a physical data warehouse, yet do it at a lower cost and faster time to value. Then we will conclude with a Q&A session to address questions from our audience and next steps recommendations. Just a couple of things before we get started. Please note that the webinar is being recorded and will be made available for on-demand viewing afterwards. During the presentation, you're all in a listen-only mode, but we will make time available for the end of the presentation to address questions from the audience. You can submit your questions at any time, typing it in the Q&A pane. The slides are available for download from the resource widget located below your presentation window. We're pleased to offer this webinar to you, and on that note, I'd like to turn the presentation over to Kurt. Kurt?
Thank you, Lisa, and welcome, everybody. I'm going to talk to you a little bit about Autodesk's journey towards our logical data lake. All right, before we talk about a data lake, we're going to talk a little bit about data warehousing, as it is part of our Autodesk strategy here. Data warehousing the IT world is well familiar with by now. A logical data warehouse, however, differs slightly from the physical. It, of course, does still have the star and snowflake schemas. It will now include possibly one or more physical data warehouses, and will also include data from external sources. But those external sources do not have to be physically loaded into your system anymore. In the logical warehouse, these are pointers to these external places, saving you the time and money it takes to load these into your physical system, preventing also then any translation structures that may have happened to that load, any discrepancies from the time it took to load, all of which improve your decision making. This will lead you eventually to a fast data strategy where things are much more timely to their source. Now, that logical warehouse that looks and behaves very much like the original physical leads you eventually to your data lake. A data lake is very much unstructured data. Think very, very large systems, very fluid in nature, data flowing in very much like a river, continuously changing things in its scope. That heterogeneous collection of data with raw data from the sources is going to be very close to those systems and is not going to behave very much like a warehouse does. So a lake needs slightly different treatment and, of course, different query systems interacting with it. A virtual layer implemented above such a lake can bring together the lake and the warehouse information into a single point presented to your end users, be they internal or external, and that single point of access now provides this lake and your warehouse as a logical concept where everything is accessed through logical objects, procedure calls, pointers, views, anything that you want them to be, without having to physically construct something and then be chained to that physical construction. So this is very much the same coding that has been done for many years in your organization already, just applied in a different way. A brief introduction to why Autodesk has gone down this path. As you well know from our announcements to the public, we are changing our business model away from perpetual and into subscription. As anyone can imagine, that will require a lot of systemic changes and a lot of changes in the way our customers and even our internal people interact with our information. In progressing towards our logical data lake, there is a life cycle. And that life cycle, of course, you can start at any point on this and follow it around, as it's going to just keep leading back into itself. But we'll begin at the top. Things need to be agile in a data lake. A lake is continuously changing. You heard the mention before of data flowing continuously like a river into it and changing concepts at all times. The agile nature then of your project development is going to follow the same pattern of being able to tune itself, change your delivery concepts based on business needs as that happens. This, of course, drives your data architecture, your architecture needing to change frequently and needing to change fluidly to match what your data systems are collecting and what they need to provide to the people making the demands that are changing all the time. Your logical data warehouse is then going to be your place to provide a lot of your physical structured information. And a logical data warehouse is going to contain all of your curated objects for those purposes. So these are your traditional concepts, things that can be structured, things that can be predictably modeled, and so on. Once you have a logicals area, you're going to need a common entrance point, an enterprise access point that is something that everyone inside and outside your company is going to pass through to get any information. You do not want to have to expose dozens of different source systems that are changing rapidly as the point of contact. Your point of contact would then change with every one of those changes to the sources. Data virtualization over that single access point allows you to give any structures or unstructures that you want, any non-structured information, big data, any traditional transactional system data, any dimensional work, any master data. You can provide all of these in a virtual layer that can do any number of different things with the same object in different ways that will make all of your systems talk to each other in those virtual concepts without your having to code those original systems. This now leads you to that logical data lake. Your systems are independent rivers, independent trickles of information pouring into the lake all at once, where the lake brings them all together, mixes them all, and this then will lead you to a world where your information is commonly available to everyone and fully interactive with itself. Once that happens, that will then, of course, drive your agile development and your agile project needs, because now that you have all of your data interacting with itself, that process cycle is going to drive changes to itself. Feedback will come into it, machine data learning, and so on, which will change your demands for what you get out of it, and we're back into the cycle again. Our business problem to change from a perpetual to a subscription model, of course, means that we have new business systems, new business models, new transaction concepts, new ways of interacting with our customers. But that's just the specifics to us. In general, and Gartner has noticed this as well, anywhere in a company, people need information. And while we are going through a transition change, and so there's a greater need for specifics on that information, if we remove the specifics, your IT department needs information, your business departments need information, your marketing areas need information. You need to make decisions on it. You need to decide on the right technologies. You need to have the management and governance in place. And that's for any kind of business problem needing data. So let's take a step back and recognize that if Gartner has noticed this, and this is a common thread everywhere, then perhaps every company is in the same boat, and every IT department in those companies is in the same boat, and we are all dealing with very much the same problems and the same concepts and the same needs and the same errors and the same problems with governance and so on. In which case, discussing these models is going to help everybody, which will in turn also help us at the same time. So, now that we are talking about the specifics of our structure, and we all understand that we're going to try and learn the same things from it, what exactly do we have going on here in Autodesk? Let's start with the philosophy. We need to get at our data, and we need to get at it near the source. We need to get at published logical data interfaces, those common objects I spoke about in the lake. We need to implement these interfaces, and we need to make sure that it's only the concern of your IT department. None of your customers need to know what's going on or how that goes on. They just need to get it. And by the very nature of these modular programs and these objects that we're making common, they need to be agile to change frequently, since your customers now with a single point of access are going to be demanding every change through that single point of access. And once that access is working, of course, any legacy systems that were not supporting it can start to go away. Let's take a look at the endpoint, shall we? As you can see on the left, you have multiple data sources of any kind, structured, unstructured, and so on. We have web information, we have transactional information in traditional databases. You can see we have some of our legacy systems sitting in physical warehouses, and yes, that's plural. And most companies out there will notice that they actually do have plural warehouses, plural data marts from those old legacy systems. We're also introducing Spark as our engine over our data lake. The both can, as you see on here, coexist at the same time, as we have not yet fully transitioned everything over to the New World concept. We're going to go through, and currently are going through, a period where these do coexist together and do work hand in hand together. And so the promise and the actual delivery of the data lake requires that virtual layer. For Autodesk, that is using the Denodo software, providing that virtual layer so that we can communicate with a legacy system, we can communicate with our new Spark system, we can communicate with anything we need to introduce to this ingestion and consumption chain, and have it all provided through that layer so that on the far right, our end consumers who have been working with some of these tools for the last 15 years on our legacy systems can continue to work on those same tools, some of them new, some of them old. But they will continue to work with new and old data without having to change anything on that tool or anything in the data to make the tool work, all thanks to that virtual layer. So what does that all look like as we get it rolling? Let's take a look back in time. 15 years ago, or heck, even 5 or 10 years ago, or less than that, there is no logical data lake. There is no virtual layer yet. We have only some structured source data that we've needed to make structured because we're working with a traditional data warehouse when it's implemented for the first time and getting your data marts and reporting rolling, and your reporting systems connect direct to your data marts. Any change to this model is, of course, going to be difficult. If I introduce new structures, I need to introduce new consumption and physical platform changes to get that new information structured properly to match our warehouses, and then get things structured properly to match our reporting systems for what those need to do. Let's start not by introducing our new business model, but by introducing our virtual layer. What happens now? Well, that virtual layer has been a one-time change to our endpoint. Our endpoint can now consume from that virtual layer. It's presenting the same things it always has before, and maybe it's got some slightly different names for canonical models or some common objects for people. Now we're going to introduce a whole bunch of those new sources for the new world and all those fun REST JSON sources and Spark sources and everything else that we need to do in our new world of doing business for our change. Notice what did not change on the slide, anything on the right half. Because we've introduced the virtual layer previous to introducing our new business models, any of those new models can simply be plugged into that layer, which our reporting systems are already connecting and reading from, and they don't even notice a change. No one has to introduce or figure out how to introduce to any number of a dozen of end-user tools how to talk to Spark now that Spark has arrived, and so on. And there's one last little piece here, of course, removing your old systems. Notice what did not change yet again, the endpoint systems on the right. The virtual layer is providing us all the information, and in the future, so now I've skipped ahead a few years, once our legacy systems have been entirely replaced with our data lake strategy, we can just turn them off. They stop feeding through the virtual layer, but the reporting is still using the virtual layer and all those common objects. It just only has to pick up from Spark now, or wherever else our data lake is going, or anything else we've had to change to get there. And a quick reminder, don't think that virtualization is limited just to the right half of the slide. Virtualization can also be an effective translation to get those sources and consume them and provide them to your data lake. So what does the ecosystem in that lake look like? A lake is more than just water. It has fish, it has plants, there are rocks on the bottom. Let's look at some of the various organisms in our ecosystem. Of course, on the left, we begin again with our sources. And so we're going to be consuming these sources in a data river fashion, and that river is important because data will continuously flow. You will not simply be running batch jobs on everything anymore. There will be live, continuous feeds of data into your big data ecosystems. Think of usage information. That's going to come in continuously. Think of constant live media broadcasts or even game interaction. None of this is done in batches. These are all happening live. And that river is going to continue to provide data into your lake, and you need to be able to handle that. Once that river is activated, and it's providing your information, of course, you're going to need your storage. You're going to need translation of the storage. Over in the middle in our archive and transform layer, you're going to notice our Spark ETL layer and our Spark fast access. So we have our physical construction to provide objects. We have our fast computation layer to cache pre-aggregated information, or even to provide aggregation on the fly as it's necessary. Data storage going back and forth through Hive and S3 to provide communication from all sources. We can get our data APIs in the Spark layer to provide any other machine interaction, and our virtual layer to provide interaction with our human beings and other systems through any of our reporting or any of our external access points. And a quick reminder that, again, that virtual layer where we are using Denodo can drift to the left. Let's assume your Cassandra imports, for example, where we have our CSE. Let's assume there is some sort of vendor that is not quite compatible with that yet, but they're providing an interface. Well, let's connect the interface to the virtual layer, translate it into something that our Cassandra imports or any of your other imports in the ingestion layer in your river can interact with to that virtual layer. So this can spread throughout your slide. It is not necessarily a single-use point. So do be aware that your virtual system can take that virtual umbrella and extend it over more than just your lake, but also to the rivers coming in. So now that we've seen the ecosystem and how the little pieces all come together, let's take a little bit more look at Autodesk's journey and getting that data lake to do a data lake's work. Your first and probably one of your most important pieces is that it's got to be usable. This needs to be the single point for everything. Otherwise, it's not really a lake. It's more of a pond or even smaller, a puddle, and you're just going to have lots of them, and it doesn't really solve the problem because that's the problem in the first place. So everything should come through here, and it should come through here in ways that everything can communicate with in as many ways as they want. Your integrity, you must publish things. You must publish what you need people to access, and you must govern it closely to your business teams. So this is where IT steps back a bit. IT has provided the mechanisms, but it is your business teams with the brain power in what this information should be doing, and they should be very well engaged with your governance and your quality assurance. As you take that common data lake for everything, your enterprise access point, your single contact, this must always be available, obviously. It's got to always be on, and everyone has to go through it. Those two concepts give you a very nice access system. With that single point for authentication, authorization and audits also happen on that, and everything is very tightly controlled for your auditors as well as for your own internal systems to be able to provide access in the first place. You do not want to have to provide access to every single system underneath. It's the entry point, the concept of a badge getting you in the door to your building that you want to have. The data virtualization concept added to the lake now is system agnostic. It does not matter if you, for example, have an Oracle database and a Teradata database somewhere feeding you transactional data for all of your incoming money. You don't need to care that they're two different systems. You don't need to worry that you don't have to code them to talk to each other. The virtual layer will handle all of that. Let them do what they do and let them do it well. take any of that additional structuring outside. Now that it's system agnostic and people are making decisions based on this, they're going to have changes to your work. Your system, because it is now modular programmed in that virtual layer, gives you the ability to respond quickly. Somebody needs information connected, connect the virtual objects. No more physical action to bring those things together. Yes, you can, but it's far easier to work on those virtual objects than to completely restructure something physical. You can also support federating data. You can support data blending. And at this point, the slide should have the ... for and so on, because you can support a lot more than just these things now. You can bring your business's dreams together. That brings us to our logical data lake as a whole. We are now beyond the enterprise data lake. We have traditional data lakes. We have your heterogeneous only, and we have your physical only, and we have, of course, your structured only. The logical data lake is the place where all of these things are found as one. And again, that's the critical point there, is it's not necessarily technologically all one system. You're going to have multiple systems underneath. But to a consumer, and this consumer can be a person, this consumer can be a vendor, this consumer can be a machine. In their concepts, there is one lake. By having those things all together, that virtual object construction gives them that experience. You're going to be able to blend your disparate, your heterogeneous, your structured and unstructured. Everything will come together in that virtual layer, and it no longer matters how they were coded or how they are behaving underneath. By bringing these things together, you're going to give your business the information they want. And that's kind of a key point, the information they want. Your business is always going to want things that are technologically difficult. Virtualization makes those much easier. Now that we've approached our data lake in the right ways, we have a single origin for all of our information. And because we have a single origin for all of our information, we know where all of our users, all of our contacts, all of our vendors are going to interact with us, and so we can prepare for the same thing. So did this meet our philosophy? Well, we are accessing the data at the source with no ETL to construct physical replication of vendor sources. We've published our logical data interfaces in common objects, virtual objects, any kind of modular programming necessary that these things can be swapped and moved and reused. We've implemented interface with our IT department. Our business teams don't have to code anything. Our source teams and our business model folks, the ones creating all of our transactional systems, don't have to code their systems to meet the IT needs. IT simply collects the information and brings it together on their own. We can bring whatever technologies we want into that solution. Agile and opportunistic retirement of legacy systems means we can turn anything off at any time, and the virtual object ecosystem will continue to respond with what it has. Have we completely wiped out a system X? It's still there, but it's no longer feeding data. Our virtual object is perhaps a union of a table from that system and a table from our new system. If we turn off the system X, it is now a union of one object, which has all the data in it and is providing normally. This is exactly what the virtual lake should be doing to provide that retirement opportunity. Now let's take a look at some of the deeper points of building this agile data architecture inside Autodesk. So we'll give you a little bit of behind-the-scenes look from our company. What did we encounter as we actually did this? The second hardest thing we had to do, number 2 on the list by a wide margin, was identifying the enterprise data sources. And this is much more difficult than it sounds. When you think, what is my customer? In a company with 10 people as your customers, that's very easy to know. As those companies get larger by orders of magnitude, it's very common that customer, for example, is sourced from multiple systems. Systems you had to get running to keep the company going. Perhaps you bought some third parties. Perhaps you acquired an entire company, merged their data. Customer is now a gray object. It comes from more than one place. There is a create button, create account button in more than one system. And that's just customer. Think of all of your data going through the exact same concept. In the larger the company, the more common that problem is. So identifying your data source will take time, but it is time well spent. Our company has very well learned that. Once this is taken care of and you know where you're getting information from, because everything is going to go through a virtual world, all of the wonderful new streaming and available technology systems, such as Cassandra and all of the very common practice now REST services that weren't so common 10 years ago, these can all be taken advantage of. And these can be dropped into your systems, and you can take the best-of-breed approach. You can leverage highly redundant cloud storage like S3. You can leverage highly redundant cloud service, cloud anything now, and your virtual systems will take care of translating that to whatever the rest of your systems were. We can take the best-of-breed for individual tiny components. It no longer matters now that an entire system has to be built and project planned for. Parts of the system can be delivered as a cloud service, and that individual cloud service part could change later because they're all going to operate on those virtual connections in the lake. Your canonical representations, I mentioned that the identifying sources was the second most difficult. The canonical representation of those same things is your number one most difficult. Those canonical representations will bring a great deal of argument to the table in your company as different departments decide what should or should not be shown and how, and they will all disagree with each other. The good news here is that a virtual object, which can be changed in minutes without having to rewrite a whole physical system, means the argument can be had, and on the table in front of the argument, someone from IT can actually model and show the results of the arguments and settle the arguments much sooner than they would have been without this concept. So yes, it's the hardest thing you'll do, but it's also going to turn out to be a very valuable thing to have those arguments. Once we have virtualized all the warehouses in Marts, now with our next generation logical warehouse and lake, any new implementations can leverage the same thing and follow a plug-and-play pattern. Any legacy systems, as I've mentioned, simply fade away. As we've architected our virtual layer, you're seeing here the actual landscape here at Autodesk. And it's going to look a little general, and that's intentional. That's part of the design of the lake. Our corporate LDAP system is feeding our authentication. It's our only authentication model into the virtual layer. Think back to the cycle slides where we've mentioned that this is a single point of access. Your data sources, we have them all clubbed there together in one little box, and they all talk to the virtual layer. It no longer matters what the other systems you have are. Everything counts as a source. Everything comes in as a source. Everything gets handled in our data ecosystem the same way by the same methods because even the sources are plug and play. Our logging infrastructure, we send our logging infrastructure, our audit logs from that virtual system because everything from your logins comes in there through one access point, log it. Everything from your data sources comes in through a single kind of communication chain, goes to the audits. Anything that changes in your system on the right with your repository and code delivery, audit those changes. They all communicate through the single point, and they all happen through the single methods. This gives your lake a wonderful logging experience for anyone using tools such as Splunk or other software that will let you go and mine those logs to see what's going on. Our source repository doesn't matter what it is. Our continuous delivery tools will continuously apply code changes in an ongoing fashion to meet those agile demands, update this view, update that object, update this web URL, send these structures forward, send that structure forward, retire this, add that. That continuous delivery will happen all the time, but it will still also happen to that virtual layer, to the same access point that everything else is interacting with. It's just a machine instead of a person, but they all have the same connections. Our consumers then are also interacting at that same level, and it doesn't matter what tool they connect with. The virtual layer responds with REST, responds with SOAP, responds with JDBC, responds with ODBC, responds with URLs, responds with lots of things. So our consumers can simply say, can I use this tool to see my data? And the answer is always yes. Go do whatever you want, just get your data here. And then we know everyone's got the same thing, and it doesn't matter what they look at it with, we've given them what they wanted. What does it take to build an information architecture in this concept? What you're seeing on this slide is a visual representation of the kinds of things you're going to need and how we've broken them out here. You're going to need base views, which are tied to your sources. And this is important. There's always going to need to be something tied to the actual objects. You're going to have layered derived views, interfaces, and so on that are going to sit between the physical concept, the DDLs, and so on. You're going to need those calculations and business rule layers and connections and joins and unions and so on. All of these things will happen behind the scenes, and they'll sit there as derived objects that can be calculated and changed and updated at any time. You're going to want to publish the actual object, so that collection should be separated from all the rest of the items doing the work. That publishing layer gives you that layer of common items that everyone in the company will be using now, and those published items are what they will interact with, and so should be no longer part of the moving pieces underneath. You can provide services and web objects and anything else that needs to run, as well as published objects that are different kinds of things. The sources are anything you want them to be, anything you need to provide the data, and that's where the meat on the very bottom of the lake, the rocks and so on that make up the whole foundation are. This is your connections to all those new systems, all those old systems, but you note they don't have to be correlated to anything else in the list. You're going to want, as you're going to see in here, there are lots of these objects and lots of these types, so the naming conventions are absolutely critical. You do not want to have one project team refer to something as customer and another project team refer to the exact same thing as account, and both teams deliver objects. Your executives will simply look at the screen and see, well, there's customer and there's accounts. What's the difference? There actually isn't. It was just a name. But you'd better give that executive one name. Otherwise, they're going to start turning away from this. And a lake that's not used is a very poor thing to have. All right, so you've seen an overview of what Autodesk has done. I'd like you to think back on some of the things we talked about being able to put any technologies you want in place and remove any technologies you want at any time without impact. That is a very liberating journey, a very freeing experience, and virtualization makes that possible. On which note, I would like to turn this over to Ravi Shankar.
That was an excellent presentation, Kurt. The key takeaway for me is that Autodesk gained agility by implementing a logical data lake, logical data warehouse, in which you were able to transition from perpetual licensing to a subscription licensing and be able to add new systems in addition to the old ones without disrupting business. In my presentation today, I will be focusing on the performance considerations in a logical data warehouse or a logical data lake scenario. That's the first question I get asked whenever people are considering these architectures. So we will talk about the different techniques that logical data lakes and logical data warehouses use and how the performance compares with that of a physical data warehouse. First, let me talk about the characteristics of a data virtualization, which is the technology used as the underpinning for a logical data warehouse or a logical data lake. There are three operations a data virtualization does. One is it connects to the source systems, and the source systems could be a plethora of structured and unstructured and even semi-structured systems. It combines the information together into a coherent result, and then it publishes back to the consuming systems, which are reporting solutions and even operational portals and dashboards and so on. There's a common misconception that the data virtualization layers actually bring all the data from the source systems, which could be quite voluminous, and combine the information in the data virtualization layer. It's quite contrary. The latest, what I call as the second and third generation data virtualization solutions, actually push down a lot of the optimization to the source systems, so that the evaluation is done at the source level and bring back only the results. It's only the very old Generation 1 systems that actually lifted these huge amounts of data, and as a result were very slow. You will notice that in this scenario, I'm going to talk about like 4 different optimization techniques that data virtualization technologies use, especially the Generation 2nd and 3rd generation technologies. Here is an example of a query that you can see at the bottom, which is asking the data virtualization solution to provide the total sales for each of the products in the last 2 years. And you have 3 different systems. You have the system in the green, which contains the product information, and let's say you have 10,000 products. Then you have the data warehouse in the middle that has like millions of rows. And then on the right side, you have the Hadoop system, which contains billions of rows. So you have your data warehouse that contains the sales information for the current year, and then the Hadoop contains the sales information for the previous years. That way, you are optimizing the storage from a cost perspective as well as from an access perspective. So the data virtualization solution, when it computes the result of this query, it will go down to the product database, collect those 10,000 rows of products, push it into the data warehouse, and issue the query to compute the result for the sales for the current year for those 10,000 products. And then it will do the same with the Hadoop system. And in each of those cases, it will bring back 10,000 results. So it totally lifts about 30,000 results into the data virtualization layer, combines them, and then provides the result, which is another 10,000 rows, back to the consuming system. As you can see, even though the data is spread across millions and billions of rows of data, the results that the data virtualization solution brings is only in the thousands. So that way it optimizes for speed and delivery of the information. And this is called the full aggregation pushdown. The second technique is called partition pruning. If you issue a query down at the bottom that says, give me the total sales for each product in the last 9 months, the data virtualization solution is smart enough to know that it does not have to go to the Hadoop system because it contains older data, in which case it prunes that out of the query and it issues the query only to the product database and the data warehousing system and lifts only about 20,000 rows of data for the last 9 months, combines them in the data virtualization layer, and provides the results back to the consuming system. So this is a very intelligent way of even further reducing the time required to fetch the results. And this is called the partition pruning. Let's take a look at the third technique, which is called partial aggregation pushdown. In this case, part of the results are computed at the source level, part of them are aggregated at the data virtualization layer, and then provided to the consuming system. If you look at the query asks the total sales for each product category in the last 9 months. So it is asking for information at the computer level, at the product category level. So the query goes down to the source system, which is the data warehousing system, and it fetches the data for all of the products for those sales information for all those 10,000 products. And then it brings the result back into the data virtualization layer where it aggregates or sums it up based on the product category level and provides even fewer than the 10,000 rows of results back to the consuming system. Since part of the computation happens at the source level, part of it happens at the data virtualization level, this is called the partial aggregation pushdown. And this also optimizes for speed. The final technique is called the on-the-fly data movement. In this case, for example, consider the query that is listed at the bottom of the slide, where you are asking the system, the data virtualization solution, to compute the discount for each product in the last 9 months. So you have two databases here. You have the data warehouse that contains the sales price, and you also have the products database that contains the list price. So the data virtualization solution lifts the 10,000 product rows along with the listed price and then pushes that into a temp table in the data warehouse, and then it computes the result between the list price and the sale price and finds out the discount, and then it just provides the results back, which is just the discounts back to the consuming system. And this is a much faster way to kind of gain access to the results rather than having to bring them all into the data virtualization layer to do the computation. So those 4 techniques optimize a logical data warehouse or a logical data lake through the data virtualization solution to provide the results at a much faster time frame. So here we are doing a benchmark study. On the left, you see the data virtualization solution that goes across the 3 different systems that I talked about that contain millions and billions of rows of data. On the right side, you see a physical data warehouse, Netezza, that contains all the information that we talked about in one central place, and it issues the same query. Now, in the next slide, we will analyze the TPC-DS results of conducting the query performance across these 2 different types of architectures. You will notice in the column in green is where the results of the data virtualization solution used in a logical data lake or logical data warehouse architecture provides. Each of the rows are the type of queries that are issued to both the systems, whether it is the data virtualization solution or the Netezza solution. And then you can see the results that are returned in each of them in the second column, and then the time that the Netezza actually takes to execute in the third column, and then the fourth and the highlighted in green column is the logical data warehouse or data lake architecture. As you can see, the timing is pretty comparable, and the data virtualization solution is able to bring back the data almost at the same time as that of the physical data warehouse, all doing that without having to move the data physically into a central location, which will take time, and also the cost of storing all this information in a central data warehouse. How is the data virtualization solution able to do that? On the rightmost column, you can see that it picks one of the 4 or more aggregation techniques for optimizing the speed, and that's the way it ensures the optimal timing. And what is significant about this is the ability to determine that technique dynamically. So best way to ensure performance gains is by using a dynamic query optimizer. So what does a dynamic query optimizer do? It uses a statistical cost-based algorithm similar to that of what you find in a database to determine dynamically various parameters in the source system, such as the row length in terms of the number of columns, the amount of time it takes to execute a query, and so on, and dynamically determine the best optimal query plan that it needs to execute and determine where it needs to execute and rearrange the query plan to ensure the best timing. You will notice in the marketplace that many other systems do not have dynamic query optimizer, and as a result, the performance will really suffer. It will not be the same as what you saw in the previous slide, where we provided the results similar to that of a physical data warehouse. It will be much, much, much slower than that of a physical data warehouse because it does not have a dynamic query optimizer. So in conclusion, we want to ensure that the logical data warehouse, logical data lake is a more optimal solution than going for a physical data warehouse and dumping all the data in there for 2 benefits. One, you do not have to move all the data into a central location, which can take a long time, months of time to do that and more resources. And the second one is the cost of storing all that information into a central data warehouse like Netezza or Teradata, which can be very expensive. So a data virtualization solution implemented as a logical data warehouse or a logical data lake, and the one that uses a dynamic query optimizer is your best architectural solution to ensuring a lower cost, a faster time to value for your solution. So with that, let me turn it over to Lisa.
Thank you, Ravi, and thank you, Kurt. Very nice presentations. We'd like to take the time to address any questions that we have from the audience. We do have some questions that have come in. As a reminder, for those of you who have not submitted any questions, please do submit them online by typing the question using the Q&A pane. All right, let's move to the first question that's come in. This question's for you, Kurt. Would you advocate a logical data lake in addition to or in place of a physical data lake?
Thank you, Lisa. It's a good question. At Autodesk, we have embarked on both, of course. As you've seen from our slides, we have our Spark big data ecosystem creating a physical data lake for us. But I would like to add that a logical data lake, since it is a set of objects, modules, pointers, connection systems, conversions, it's virtual. It has no physical storage. So unless you already have something serving the purpose of a physical data lake, you might need one. Unless your company has no such big data needs at all, then perhaps you just need to look at a logical data warehouse instead of a data lake. At least at Autodesk, the two are complementary.
Thank you, Kurt. We have another question here. I think this is more for you, Ravi. This is a benchmark study. Have any of your customers seen this kind of performance gains?
Thank you, Lisa. I would definitely say yes, and Autodesk is a great example for that. So I'm going to ask Kurt to kind of jump in and ask him to talk about the performance gains that they have actually seen by deploying the dynamic query optimizer. Kurt?
Thank you, Ravi. As you said, we have gone through a lot of performance analysis. We took help from some of our Denodo consultants, and so I can't take full credit for that. So Ravi and Denodo do get some credit. We analyzed a collection of Oracle databases and Redshift databases that we were running virtual objects over to find out where our transactional queries were starting to bottleneck and break down. We were able to identify on both systems query enhancements that could completely change the way systems work. For example, we were able to find that we were to take Oracle queries and simply change the way we were asking for the query. No other indexing, no other joining, no tables, no stats, no nothing. Just change the way the query was asked and get 3 times better performance out of that. And then on the Denodo side, we added the optimization stats. We added cost optimization to the system in Denodo, and we were able to get another 10 times benefit out of that. The actual figures were a 1-hour query, 3 times better down to 20 minutes, and then 10 times better down to just over 2 minutes and 20 seconds. So those were the specifics behind our transactional queries resulting from that. And it was entirely because the virtual tool allowed us to do all kinds of query tracing, tuning, change this, change that, be able to put those objects in place where the physical systems couldn't allow us to restructure anything to play with it.
Oh, thank you very much, Kurt. Question for you, Kurt. A benefit for a physical data lake is schema on read. Can the same benefit apply for a logical data lake?
Thank you, Lisa. That is a tough question. It can apply if you design it for that purpose. A logical system implies that you have some sort of planning and preparation in advance for the way that you are going to deliver your common objects, deliver things for your people to use, and so on. If you want to plan for them to have the schema on read, you can, of course, deliver the array structures and so on that will simply nest themselves properly. But it does seem to be a little counterintuitive, and it feels that way, that a prepared system with all those public objects would not have dynamic structures underneath as you've already prepared the system for consumption. So the two do feel like they go separately, but they can go together. It will take some work to get you there.
Okay, thank you, Kurt. Question for you, Ravi. Why other data virtualization solutions do not have dynamic query optimizer?
Okay, that's a great question. I would say it has to do with the heredity of the solution by the vendor. Some solutions are have been an outgrowth of a data integration solution from some of the large vendors, in which case they use it more from a data federation perspective rather than a data virtualization perspective. So they do not optimize the queries for performance at the source. Instead, they lift all the data into the central data virtualization layer and then combine the information. And the reason for that is, even though I have told that the performance will be really bad in such a situation, the customers of those solutions do not deploy them as data virtualization. They use it for prototyping before they can actually do a ETL mapping. So in which case they're not worried about the performance gains. They're just doing it for prototyping, so it works fine. And in other cases, though some systems might have a performance optimization at the source level, it might be more static. That is, they might not be doing it from a dynamic runtime perspective. And then the ones like the Denodo have the dynamic query optimizer, which uses the cost-based optimization and during runtime dynamically determines the loads on the system and many other statistics, and then determines the best query plan to execute on the systems to guarantee the best performance timing. So to sum it up, it has to do with how the vendor started off with their approach for either a data federation or a data virtualization solution, I would say.
Thank you, Ravi. This next question I think would be great for you to answer, Kurt. Question is on what should a company look for in their people when they are embarking on a logical data lake?
Thank you, Lisa. That's a good question. This is less about the technologies involved. Your people, one of the first things you're going to look for is not on the technology side. It's on the business side. Your business teams have to be ready for that data lake. They have to be ready for the change of interaction, and they have to be having the problems that a data lake answers. Beyond that, again, now you're going to get to the technological side. You're going to need people with skill sets very heavily into modeling, logical concepts, modular construction. As you're dealing with a logical data lake, you're going to be dealing with a very large number of virtual concepts, none of which are actual real items. This is taking a step away from most programming situations where you have physical objects to work with. You have programs that are designed to do specific things. Virtualization is all about flexibility, dynamics, items that don't necessarily have a physical system underneath or a reason for it to be there, but it serves so many dynamic services. These are things that are difficult to learn for someone who has spent a very long time in a physical design world, but they are also things that will make that person much more productive once they do begin to pick it up. And so if your company has neither the demand for it nor any of the skills in it, it's probably not something to look for. But I would suggest looking for people that are trying very hard to take your existing physical systems and make them do things dynamically. That's a set of people that would probably fit this very well.
Thank you, Kurt. That's it for questions. I'd like to thank the audience for submitting the questions that you have submitted. If you did submit a question and for any reason I've missed it, please note that we will be sure to respond back to you later after the webinar is over. As a next step to learn more, we have some great resources on our website. We highly recommend the recording of our recent educational seminar on logical data warehouse, data lakes, and data services marketplace. We've broken down the recording of the seminar into easy-to-digest chunks of information. Visit www.denodo.com and search for Educational Seminar. You can also find valuable resources on our solutions page for logical data warehouse and data lakes. While there's some great resources available for you to learn more about data virtualization, we encourage you to try data virtualization today. We've made it easy. You have two options. One is to download a free copy of Denodo Express, which is a restricted version of the Denodo platform, or you can go to Amazon's AWS Marketplace, swipe your credit card, and access a full-fledged version of the Denodo platform. With the cloud version, you not only gain the pay-per-use pricing, but also a readily installed version of the Denodo platform. And of course, if you're ready to speak with one of our data virtualization experts, we welcome the opportunity to discuss with you how you can benefit from using data virtualization in your upcoming projects. We have reached the end of the webinar. Thank you for your participation. We do hope that you found this webinar of value, and in efforts of providing you with more webinars that will help you in your evaluation of data virtualization, we appreciate you taking the time to complete the brief survey, which will display on your screen at the end of the webinar. Thank you again. Goodbye.